Welcome everyone. Our project is called Aorta Guard, a machine learning solution designed to detect cardiovascular disease early and effectively. Let's dive in. Cardiovascular disease is the leading cause of death globally, accounting for nearly 18 million deaths annually. What's tragic is that up to 80% of these events are preventable with early risk detection and intervention. Yet healthcare systems still rely on reactive care, intervening only when symptoms arise. Meanwhile, vital signs like blood pressure, cholesterol, and lifestyle habits are captured during routine checkups and contain predictive signals that we often overlook. The goal of our project is to build a machine learning system that uses these routinely collected metrics to predict the likelihood of cardiovascular disease before it manifests, enabling timely and preventative care decisions. We selected a cardiovascular disease dataset from Kaggle containing over 70,000 clinical records. The data includes objective metrics, examination results, and subjective inputs, simulating real-world screening scenarios. We engineered and standardized 11 key features across demographics, vitals, and lifestyle factors. The project is structured as a binary classification task, predicting the presence of cardiovascular disease with an emphasis on high recall to reduce false negatives. Feature-important analysis confirmed clinical relevance with systolic blood pressure, hypertension status, and cholesterol level emerging as the most predictive features. This diagram illustrates our complete end-to-end architecture. Raw cardiovascular data is first stored in Amazon S3 and processed in SageMaker notebooks. Engineered features are then queried via Athena and stored in the SageMaker feature store, organized in logical clinical groups. Our CI/CD pipeline automates every stage from pre-processing and model training to evaluation and tuning. Batch Transform handles inference and generates monitoring baselines, which feeds into SageMaker model monitors for drift detections. Validated models are deployed to endpoints, registered in model registry, and tracked using CloudWatch metrics and alarms, ensuring performance, traceability, and operational visibility through the life cycle.
On this automatic logistic regression, in this part of our project, I focused on implementing a CI/CD automation workflow for our logistic regression model using AWS SageMaker. We developed and executed 3 code scripts: train_logistic.py, which is a Python file for model training, package_model.py to compress our model and inference logic, and deploy_model.py for model deployment and batch inference setup. The workflow used Python, Scikit-learn, S3, and SageMaker. Model artifacts were versioned and stored in S3. This helped establish a modular and automated flow that aligns well with enterprise-level MLOps practices. Here you can see a sample training job kicked off using the Scikit-learn estimator in SageMaker. We used feature engineered CSV files stored in S3. Once training is triggered via the CI/CD workflow, the model artifact is generated. The package block shows how we bundled the model with its inference script using the tar file module, enabling modular and reproducible deployments. So here is a snippet from our train_logistic.py script. This script reads the feature engineered CSV from the S3 input path and trains a logistic regression model using Scikit-learn. The train model is serialized and saved for packaging. This code is central to the CI pipeline, ensuring model consistency and reproducibility. Next is the package_model.py file. This script compresses the train logistic model along with the inference.py script into a tarball format accepted by SageMaker. This modular packaging allows us to plug the model into deployment workflows while maintaining clear separation between model logic and deployment logic. So the deploy_model py script initiates model deployment and sets up a batch transform job. It specifies as model container parameters, S3 paths for input and output, and IAM roles for permissions. However, we faced several issues, most critically failures due to /ping health check errors, which I will explain in the later slide. Training job trigger with SKLearn estimator. So this block shows the CI/CD trigger where we launched the training job using SageMaker's SKLearn estimator. It consumes the CSV data that includes our engineered features and kicks off the logistic regression model training. Once the job completes, it saves the trained model artifact in S3, which can be packaged and deployed later. This estimator block essentially forms the core of our automated pipeline, enabling repeatable training every time the new data is introduced. So here we encountered real-world deployment challenges. Although the training job succeeded, our batch transform jobs consistently failed. The model container failed the /ping health check even after we tried various fixes like switching between job_lib and .pkl, removing the custom inference.py file, and verifying the IAM roles. These errors helped us better understand the limitations and requirements of SageMaker's model containers. This screenshot shows the CloudWatch logs. We confirmed that the training job succeeded and examined the transform job logs for clues. We verified the IAM roles, bucket access, and the S3 path. This helped isolate the issue to container level incompatibilities with our inference setup. So for the future enhancement, looking ahead, we plan to fix the /ping health check issue or switch to real-time endpoints. We also aim to build a full SageMaker pipeline for DAG-based automation. Further improvements include logging evaluation metrics, setting validation triggers, and enabling auto retraining when data shifts. So finally, we assessed risks in both technical and ethical domains. On the technical side, versioning issues or container compatibility may arise. From an ethical standpoint, predictive bias in healthcare ML models is a serious concern. We recommend fairness audits and transparency in communicating model limitations to end users and stakeholders. Thank you.
Thank you, Prema. In this slide, we're showing the process of creating SageMaker Feature Store and organizing our data set into feature groups. First, the feature group object is initialized. This implicitly provisions the underlying feature store service. Next, we register each feature group using fg.create, specifying the schema, record ID, and event timestamp for tracking updates. We then define 4 logical groups, which is looped through and created accordingly. Finally, the engineered features are ingested using fg.ingest, populating both the online and the offline store. To the right, this is how we logically organized our engineered datasets into 4 feature groups. The demographics group include core population identifiers like age and gender. The vitals group captures physical measurements such as blood pressure and BMI, all critical indicators of cardiovascular stress. Our labs and lifestyle groups reflect metabolic and behavioral risk factors, cholesterol, glucose, smoking, and physical activity. And finally, the target group stores the cardiovascular disease label, which serves as our predictive outcome.
Thank you, Ms. Thai. This slide highlights the model and data monitoring setup for our system. We enabled data capture using SageMaker's data config, allowing us to track both inputs and predictions during inference. These logs are stored in Amazon S3 and connected to CloudWatch for visualization. The image here shows the actual monitoring output, helping us to detect issues like data drift or input anomalies over time. This setup ensures our deployed model remains consistent, reliable, and auditable, critical for regulated domains like healthcare or finance. So this code block sets up CloudWatch monitoring using the SageMaker data capture config. By enabling full data capture, we can track all incoming requests and outgoing predictions, which is critical for auditing and debugging in production deployments. We monitored all jobs using Amazon CloudWatch. Here, we confirmed that our training jobs ran successfully, while transform jobs revealed failures tied to container health. The logs helped isolate issues such as missing endpoints or container response failures, reinforcing the need for observability in ML pipelines.
Thank you again, Prema. In this CI/CD DAG, we demonstrate how our pipeline accounts for both success and failure at key stages. We use try except blocks to catch and print errors during training and batch transform, which helps identify exactly where the failure occurred. For example, if the model fails to train or the transform job doesn't launch, the exception is raised and logged, preventing the pipeline from silently failing. This improves the overall resilience of our SageMaker automation and aligns with best practices for modular, fault-tolerant ML workflows. Unfortunately, due to the AWS service crash and reaching our budget limit, we were unable to complete the final batch transform steps. Although not yet fully integrated, we plan to use SageMaker Model Registry to streamline our post-deployment model management. The registry would serve as a centralized catalog for storing metadata for both the logistic regression and random forest models. Once registered, each model version would include performance metrics like AUC and recall, source training code, data lineage, and approval status. This enables rollback to earlier model versions if performance degrades. The support auditability for compliance. Integrating model registry into our CI/CD pipeline would have allowed automated registration of each successful training job output, facilitating a seamless transition from evaluation to staging and production. This feature is still in the backlog and will be a valuable enhancement for future iterations.
So here we are setting up the batch inference process using SageMaker's transformer class. This code configures our deployed logistic regression model to read input data from an S3 bucket, run predictions in batches, and save the results back to another S3 location. We used a single record strategy to handle row-wise predictions and accepted CSV input to maintain consistency. One challenge we faced during this step was ensuring the right container responded correctly and paths are properly defined. This was critical to successful deployment and response formatting.
Thank you, Prema, and everyone for watching. This concludes our presentation.